Hello everyone, welcome to topic 3.5, kinetic molecular theory. In this you should be able to explain the relationship between the motion of particles and the macroscopic properties of gases with kinetic molecular theory, particle models, and graphical representations. So we're going to cover those in this. So, starting with our notes, kinetic molecular theory is a simplified model that describes the nature of gases. It is a series of postulates that are based on ideas or theories that are based on speculation about the behavior of each gas particle. Here are the postulates as they relate to an ideal gas. The next section will address deviations from that, or what happens if it's not ideal. But for ideal gases, the size of a gas particle is so small compared with the distances between the particles that the volume of individual particles is negligible. That is to say that it is so small that the volume of gas particles can be ignored. Gas particles are in constant random motion. They move in straight lines until they bump into each other or the walls of the container. When the particles bump into the walls of the container, this results in a phenomenon that we know as gas pressure. And these are completely elastic collisions is the general idea. That means that when they hit, they don't lose energy, they just bounce off in opposite directions. The particles are assumed to have no attractive or repulsive forces between them. In other words, the effect of intermolecular forces can be ignored for ideal gases. The average kinetic energy of a sample of gas is proportional to the Kelvin temperature of the gas. So kinetic energy, remember, is 1/2 mv squared. Ooh, look, that's physics. Where mass is m and velocity, or the speed of the particle, is v. Okay. And so there's an image of gases moving around and bouncing. Coming back to some gas laws, over the years scientists have studied gases and noted how they act under different conditions. There are several gas laws that look at how one variable changes when another is varied. So it's comparing only two variables out of the ideal gas law: pressure, volume, temperature, moles. Only two are looked at. The table below summarizes some of those laws, and these are the ones that are most likely to appear on the test. Okay, and the relationships for those. So we have the equations, and then we have the relationship as well. Okay, if we combine all of these, we end up with a combined gas law. A lot of the times, moles is omitted, or taken out because it does not change if you're using it. The Maxwell-Boltzmann distribution, now this one is a pretty big part of gas law in kinetic molecular theory. This shows the distribution of the kinetic energies of particles at a given temperature. So, like, if they graphed and plotted all of the speeds of all the particles in a sample, it would give them this. As you look at the Maxwell-Boltzmann distribution, you can see that it skews to the left. The tail on the right, I think that's supposed to be right, is much longer, if you see that over here. Okay, so it stretches to the right, but it is skewed towards the left. At the origin, the speed is 0, and speed cannot be less than 0. They can stop moving, but they can't reverse time. By increasing, so we have this is our speed, so that relates to our temperature. So cold gases on average have a lower temperature than room temp, or lower speed than room temperature than gases, or hot gases, sorry. By increasing the temperature of a gas, the distribution of the particles shifts to the right. Notice not every particle has the same energy, right? It's an average. The temperature measures that average kinetic energy. the temperature of the first gas here is greater because you see more like wiggles. You could also draw these with longer arrows, which is how I would draw them, showing that it's going that way really fast versus maybe this one not going so fast. So the temperature of the first gas is greater than the temperature of the second gas. The mass might be the same, but the velocity differs. So because they have the same mass, but their velocities are different, their temperatures will be different. So remember that kinetic energy, which if we take the average of that, we see that as the temperature in Kelvin, that is equal to 1/2 mv squared. The average only applying if we're looking at temperature, and we average all of those kinetic energies together. In this example, the mass of the particle differs, but the velocities are the same, right? So they're both going really fast. This also results in a different kinetic energy. So for this one would have the higher temperature. Okay, because even though they're both going the same speed, the particles in both, because this one has a bigger mass, and if we look at the kinetic energy equation again, if these are the same in both, but this one is bigger in the green, we're going to have an overall larger kinetic energy. So remember that both mass and velocity affect the kinetic energy of particles. The formula for calculating kinetic energy, Ke equals 1/2 mv squared, where m is mass and v is velocity. The mass, and I think this is also on your guys' equation sheet, the mass of the particle is in kilograms and the velocity is in meters per second. Kinetic energy is calculated then in joules, which is kilograms per meter second squared, where these both are squared. Okay. This relates to the rate of effusion, which is the ability to diffuse through a small hole or across a specific space. And this is related to the size of particles. Graham's law, another dude, describes this relationship. Okay, and so we have that here, rate of effusion. Okay. We can see that as particle size increases, the rate of effusion, or how fast it spreads out, decreases. So if it's a bigger particle, it's going to spread out slower, given everything else, if you're comparing them, is the same. So let's do some I do's and we do's to start reviewing this. So given a sample of hydrogen gas, hydrogen chloride, and chlorine gas at the same temperature, place the particles in order of decreasing average particle speed. Okay. So thinking about this, if it is low mass, then it must have a higher velocity to have the same kinetic energy. Okay, and we're talking about speed, so that's velocity. So if it has a low mass, it must have the same. So the ones that are going faster have to be lower mass, so that way they all end up being the same temperature. So hydrogen gas has to be going faster, so we're going to rate these in order of decreasing size. Cl2. Okay. Now for the we do, consider, I don't know why I just want this one. Consider an equal molar mixture of gases, H2, N2, and F2, placed into a container with a pinhole opening. After some time has passed, place the gases in order of increasing amounts remaining in the container. So we need to remember that from Graham's law, the smallest diffuses the fastest. right? So the one with the least remaining would be the smallest, so that would be H2. And then we would rank them in order of their size. So N2 is the next smallest, followed by F2 being the largest. So it would diffuse or effuse the slowest and have the most remaining. So using the concepts covered in kinetic molecular theory notes, you're going to answer some of these or drawing the questions in the you do. Check your work, and thank you for tuning in.